it again and get the correct copies. So can I have somebody explain to me what you understood by flow control, or as much as you understood? This is not a test, so you're allowed to make mistakes. Hashim.
Yes.
Tell me what you understood by flow control. What it is and how it is achieved at the transport layer. Hashim? I thought I heard Hashim say yes. Somebody?
I can try.
Okay, who's speaking?
Wisdom.
Okay, Wisdom. Go ahead.
Flow control is managing the amount of data that is transmitted in the communication between two nodes. It is done by, it is mostly done to ensure that the receiver is not overwhelmed by the sender of information, so that they can information is not lost by the receiver because it's overwhelmed.
Okay.
At the transport layer, it is done using window size, a buffer that the receiver maintains, so that it advertises to the sender that buffer as the data is sent. Each time the sender sends any data, the remaining buffer size is sent back to the sender using an acknowledgement. The acknowledgement first of all acknowledges that it has received the data, and it also contains the remaining buffer size, which the sender can use to know how much it can send at within any given communication.
Good.
Okay.
Why is it done that way? And I'm not asking you that to Wisdom, I'm asking that to the whole class. Why is it that it is somehow different from what we saw in the original sliding window protocol? There was no issue of window size, it was just an acknowledgement. So why is it done differently this time? In other words, why is there a difference between the sliding window in transport layer and the sliding window in data link layer? Can I have somebody? Because I thought I spent time trying to explain that, but a lot of time was spent on that particular topic. Oh, you never heard me say anything about it? No, when you keep quiet, you're not helping yourself. I think I'm trying to help you, but you don't see it. You're not helping yourselves. Because remember, I've just told you the cat is coming in 2 weeks' time. Is it a week or 2 weeks? But if I ask you in the cat, you will have an answer, I guess. If I ask that question, not that I'm going to ask it, but if I were to ask it in the cat, you would have an answer, I guess. All right. Since you don't want to talk, you just want to listen. So it's okay, you can listen. Whether it makes sense or not, we don't really care. So I'll skip everything there and I'll go to the next topic. Failure recovery. Now remember, we are doing data transfer at the transport layer. We've said that there is flow control, there is error control. However, there's also the possibility of failure and therefore the need to recover from failure. I think I already explained, or at least I think we talked a little bit about this type of failure. But there are two possible failures, host failures and router failures. But we'll start with the one at the network layer, that is the routers. Now they can fail whilst the communication is taking place between two applications. And it really depends on what type of network layer you're using. If you're using the connectionless type of network, and remember I'm talking about the network, not the transport layer. But you ought to remember that the network layer is used to carry data for the transport layer, because the transport layer only exists on both ends. So it is actually the network layer that carries all the data from one transport layer to another transport layer. So if that network fails, then it can affect the transportation of data from one application to another. Now, if the network is connectionless, then it really doesn't matter. It really doesn't matter because you can always recover from the lost transport data units. Because in a connectionless network service, obviously you know that the network is able to reorganize itself and find another route. So if at all there is a failure, then another route will be found. And if it is connection oriented, if the transport layer is connection oriented, and remember connection oriented network layer is where we have the virtual circuit. The virtual circuit is like a circuit that is created end to end, and data pass through the virtual circuit in the order in which it was sent, and every packet follows the same route. So obviously, if there's a problem with that connection, then you have to terminate it and establish a new one. And then, of course, the transport layer can then request for data which was lost. But there's need to know that as you transport data through the transport layer, some failures can make it difficult for data to go from source to destination. And depending on what type of network layer you're using, you can either recover dynamically, or you may recover by just terminating the connection and starting afresh. That is as far as the routers and the network is concerned. But what if the host itself crashes? Remember, we are really interested in applications here. So applications are running, but they're running on top of the transport layer. So we are basically saying that if the machine on which an application is running fails, then what? So remember that one application has already created a connection to another application on another machine, and then it fails. Then what? Then what happens? Now, if that happens, we end up with something we call a half-open connection. And what is a half-open connection? This is a definition from Wikipedia. The term half-open refers to a TCP connection whose state is out of synchronization between the two hosts, possibly due to a crash on one side. So they're out of sync. And they're always in sync based on the sequence numbers and the window sizes, which we have just been told. That's how they synchronize what they're doing. But if one side fails, then they're out of sync. Now, why are they out of sync? Because when the system upon which a transport entity is running fails and subsequently restarts, then the state information of all active connections is lost. In other words, the side that fails loses all the information that was in memory. So assume there's a connection between two applications. Assume they have created a transport connection. So there's an application on this side, and there's another application on that side, and they're using that connection to communicate. Then one side fails. So the machine on which this application is running here fails. It goes down. Then what happens? Then it means that everything that was in memory is lost. That's really what it means. And remember all those things we've talked about, like the window and what the window size is, and what was the last number of bytes that was sent. You know, what are you expecting next? All those things are kept in memory. They're not kept on disk. They're kept in memory. So if the application, if anything happens and the machine fails together with the application, then all that data is lost. So even if you restart the application has no data in memory. In other words, this connection is really destroyed. By that failure, this machine does not know about this connection anymore, because all the data that had to do with that connection goes down with the failure. So what we end up having is what we call a half-open connection, because the connection is only open on one side. Only the application that didn't fail knows about this connection. So it is half open. On one side, it's open. On the other side, it does not exist. So what happens? Because this application here was communicating with the other one, so it may continue to send data, but the other side is really not aware of what it's doing. So it may continue to communicate thinking that this side is also aware of what's going on, but really it is not. So how then do we get out of that situation where we have a half open connection? Basically, the idea is that we have to close that connection. I mean, there's no other way. It has to be closed. But it will only be closed on the side which still has the connection open. On the side that failed, the connection does not exist, really. So the side that still thinks the connection is open needs to become aware that the connection doesn't exist anymore. And so it needs to terminate that connection. Otherwise, no communication will continue to take place. So how exactly do we make that application to terminate its side of the connection? So it can use something we call a persistent timer. Now remember, when it is half open, as I said, it will continue to send data because it's not aware of what has happened on the other side. The failure that has happened, it doesn't know. So it will continue to send data. And of course, no acknowledgement will come back. So it will need to set this thing we call the persistent timer and continue to send data, and hopefully wait for an acknowledgement, which we said will not come. So when the timer expires, then it should come to the conclusion that something is wrong with this connection and abruptly terminate it. Okay, by telling its application that this connection seems to have a problem, so stop sending anything. So remember, on this side, there's a transport layer and there's the application that's running. In fact, let me draw it this way. There is a transport layer and there's an application that's running on top of the transport layer. So it's the transport layer that knows about this connection. Any data to be sent is sent to the transport layer. So the transport layer should really set a persistent timer, because every time it sends some data, it expects an acknowledgement. Now, if it notices acknowledgements are not coming, you should set that persistent timer and then resend or retransmit the message a couple of times. And if after that maximum number of times it doesn't receive any acknowledgement, which is actually what will happen, then it should tell the application. You should tell the application that this particular connection seems not to be working anymore, so that the application can then know what to do. So what I'm saying is that, well, it will terminate the connection and tell the application that this connection is not working. So we can use the persistence timer to close the connection and signal to the application that something is very wrong. Alternatively, you can also use this reset function. Now, this ideally means that the failed side. Now remember that this side will send some data, will continue to send data. So data will arrive this side and it will arrive at the transport layer. It will arrive at the transport layer. But because the transport layer has no connection created, ideally it should send a reset. You should look, I even have no connection with you, so I don't understand why you're sending me data. So you should really send a reset, what do you call it? A reset message back to the sending side. And basically that's a reject message, or something that tells the other side that, look, this connection is not valid, let's just terminate it. So when the reject goes back to the sender should look at the number that is on the reset, because the reset also has an acknowledgement number, because this message that was sent with a sequence number. Whatever that sequence number was will be in the acknowledgement of this message. So it will be an acknowledgement and a reset at the same time. So it will send the value that was in the request message, plus it will say, it will set the reset bit. So when it goes back to the sender should first of all look at the acknowledgement to confirm that it had actually sent a message like that, a message with such a sequence number. And then it should notice that it's a reject and realize that something is wrong. The other side does not recognize this connection. And based on that, it can then terminate the connection. That is, the side with the half-open connection should really terminate. When it gets a reject message, it should then terminate. You should realize I'm sending messages, but the other side is rejecting it. Okay? And then it will do what we call an abnormal termination, and again, explain to the application that something has gone wrong, and so we have to terminate the connection. Now, why are we having these half-open connections? Because we know that machines can crash, they can fail for whatever reason, and that can happen during a connection, during data transfer. So it will create that situation. And if you don't do anything about the half-open connection, then it means that this application will remain running. This application will remain running with the connection which it thinks is open, sending data and never getting responses. And in that situation, they are really not communicating. It is trying to communicate with a side that is not responding back. And it's not a good thing. And more than that, it is consuming resources because it's consuming memory for nothing. So it's a good thing to terminate a half-open connection because it's not helping anybody. And that brings me to the end of this data transfer phase. In the data transfer phase, we've talked about flow control, we've talked about error control, and I think there are enough examples here in your notes, which you should look at and try to see whether you understand error control, whether you understand flow control, and this, what I'm now calling error recovery. Now, remember that in this part, we should really have talked about what I called congestion control. It's a whole huge topic on its own, and I really don't think I want to talk about congestion control, but it should really fit here. So if it's something you feel you're interested in, please read more. As I've said, it is not something I'll bring in the card or in the exam, but it's good to read about it. I will only be concerned with the flow and error control and failures that may occur when data is being transmitted. So unless you have any questions, I'd like to move on to a new topic. Any questions? Mm-hmm. Mm-hmm. That's a good question. I wish I could answer you. I wish I could give you the answer, but maybe it's good to look at how TCP implements. It may be good to go into the TCP protocol and find out which one they implement. Possibly they use both. I just imagine. I don't know. But let me give you that as an exercise. You just need to look through the TCP protocol and find out which solution do they use to deal with the half-open connection. I suspect they use both. But do you mind checking for me and telling us next time? Please, just remind me your name again. Robert, I can't quite see. Roman, okay. Roman, please, let me give you that homework. I don't think it will take you a long time to find out that. Since you know both solutions, you just need to find out what TCP uses. Just go to a topic called half connections, half open connections. Now, I don't know whether I gave you, I don't know whether in the classroom there is a link to this textbook. Is there a link to the textbook called, let me find out what it's called. There's a textbook called TCP/IP. I should have really given you a link to it. I don't know if you have seen any textbook like that in your classroom. Have you? That would be a good textbook to check. But there should be a link, and if it's not there, I will put it at the end of class. It's a textbook called, I even think I gave you that title in your assignments. In one of your assignments, a book is there, but I think it's called something to do with TCP/IP.
Madam, someone sent it in the class group earlier today.
Somebody sent what?
Sent the link of the PDF in the class group.
Yeah, that's a good textbook to have. So I'm just saying, Roman, if you can just go to the TCP section and look for a subtopic on half connections, half open connections, you should be able to quickly get an answer to that question. And then you share with us next time. But thank you. I think somebody has just said that link has been sent in the class. That's a good book. As far as TCP and UDP are concerned, that's a good book to look at. So it will probably help you understand better what I have been trying to explain. If you have not understood what I have said, that book can help you understand it better. Okay, so shall I take it that we can move on to the next topic unless somebody has a question? Yes, Gregory. Yes, go ahead. Hey, Gregory.
At the beginning of the class, you asked us about the difference between the sliding window of the data link layer and the transport layer.
Yeah.
And maybe we didn't give responses to it, but I would like to give what I remember, and then maybe you can clarify and we can finish on it. What I heard from the previous class was that
is there anybody else having their mic on? Because there's a lot of echo. Gregory, we can hardly hear you because of the echo. So I'm trying to get everybody to shut down their mic. Is there anybody else with the mic on? Okay, you try again. You see if we can hear you, Gregory.
Can you hear me now?
Yes, I can hear you.
Your mic is muted, so I've seen you try to talk, but you're muted.
I have muted, so I think everybody's muted. We are just listening to you. Go ahead.
Yeah, so I was asking, at the beginning of the class, you asked us about the difference between the sliding window in the data link layer and the one of the transport layer.
Yes, I did.
Yeah, so, and maybe you skipped it because we didn't give any responses to it. And I would like to give a response. Yeah, and I'd like to give a response. Yeah, so what I got from the previous class was that the sliding window of the transport layer is is dynamic in terms of it uses like the window size is dynamic to allow for based on the network conditions that are set, so that the I mean the flow control is controlled by having a dynamic window size, but the other one is preset and maybe preset and an exact size that doesn't exactly same. But maybe that's what I get. But you can clarify and finish on it, because it's a question that we need to know about, and maybe I'm right.
Yeah, but you have to tell me what I said in class, because I gave the answer to that question in class. Yes, there's dynamicity, but in what context? You are saying it's the network. How does the network cause the window size to be dynamic? I think that's what you need to tell us.
Maybe I'm not exactly sure about that.
Okay, let's do this.
Yes.
Let's do this. Let me give you that as a homework. And just like Roman will tell us the answer next time, hopefully you'll have found the answer. One of your classmates will have found the answer to that question. Because I think I spent a lot of time trying to explain this. Remember, we had a class where I was disconnected, and we ended up not having the rest of the class. I was trying to explain those things you're talking about. When I came back the next time, I went over that again. So unless you have just forgotten, I feel like I've spent a lot of energy trying to distinguish the operating environment of the transport layer and the operating environment is the data link layer. I'll be very saddened if I have just been talking to myself. So let me give you the chance, and the whole class at large, go and read, go and find out the answer to that question. There are 4 different topics I covered. Congestion. I think I covered the delays, the communication delays, and there are buffers and things like that. There are four topics I covered in 2 sessions of 1.5 hours. Just to tell you that it's important that you know that. So please read, and let's have some answers to that question next time, okay? Now, the topic I'm about to start, I think somebody had brought up this topic, and I'm talking about the topic of multiplexing. I'm moving on to the topic of multiplexing. And I think we had a discussion, and I requested the person who asked that question to wait until we reach this topic and ask that question again. So whoever it was, I think it was Oko, if I remember. I hope he's in class today, but even if he's not there, that question was asked, and I'm hoping that by talking about multiplexing, that question will be answered. If it is not answered, then please ask the question when I pause at the right place. Okay, so let me stop presenting this and get into that topic of multiplexing. And again, if I ever get disconnected while I'm talking, because I might not be able to note that, please call me. I hope my phone is working. So I have, as I said, I have rearranged the notes we were having only part 1 and part 2. Now we have part 3. So I've removed everything to do with multiplexing and I've put it in the part 3. Because multiplexing is not really about data, it's about data transfer, but it is not related to a single transport connection. Because a transport connection, you establish it, you send data through the connection, and you terminate the connection. So this is slightly different, although it's related to connection. So I have chosen to put it in a different topic. But it's a very important topic as well. So, right. So this is about multiplexing, and it has to do with the transport layer mechanisms that are required. I'm not so sure whether it's only required to support connection-oriented service, but it's a transport layer mechanism which is required, and we will look at why it is required. Now, this topic called multiplexing, I'm sure you've come across it, I think, at either at the data link layer or at the physical layer. You must have come across the issue of multiplexing, where you can take several signals and multiplex them onto a single channel. You can combine different signals and send them on one channel. So I believe you've already encountered multiplexing at the lower levels. But now we want to talk about multiplexing at the TCP level. Now, so you already know that multiplexing is a process of combining 2 or more data streams. As I said, you may take 2 different signals and multiplex them onto the same physical connection, on the same physical channel. But it has the same meaning where you're combining different data streams and multiplexing them onto a single physical connection. But this multiplexing is being done as a transport layer. Now, remember that at the transport layer, we are having connections. So multiplexing, when it is used within the transport layer, is we are taking all those different transport connections and multiplexing them onto a lower level channel. Which of course will then be the network channel. So at the transport layer, we have several connections, but we multiplex them or combine them into a single connection at the lower level. Now, of course, multiplexing can be used in either direction, but our concern here will be about the upward multiplexing. We will not be too much concerned with downward multiplexing. So you can read a little bit more about downward multiplexing, and the notes are really in your slides. So what are we really saying here? Notice that on this side, there are several transport connections. Let me get my pen. There are several transport connections here. Why? Because you can have several applications running on the same computer. And of course, each application will have a transport connection. If it is using the TCP, remember that UDP is connectionless. So if it is using TCP, it will first create a connection to the other application. So you may have several transport connections on a single machine. And so we need to multiplex them to a single network connection. I think I will use a diagram to explain what that means, but let me just finish with this diagram which distinguishes. Now notice that there are several transport connections, which means on each of these service access points, there's an application running. But when it comes to the network layer, they are using one network connection. So all the data coming from application 1, application 2, remember there's an application there. On each of these, there's an application that is sending data. So all that data will have to use one transport connection, a single lower level transport connection. They will all pass through that network connection. And that's what we call upward multiplexing. But similarly, you can have a single application running on your machine and using multiple network connections. In other words, it has opened several network connections, and the data that is coming from an application is being sent through several network connections. And that, of course, will be for performance reasons. So an application is sending data, but there are 3 different channels on which that data is being sent. And so obviously you realize that that communication will be faster. So, but we are not going to look at that type. We are going to look at this upward connection where you take several applications and whatever they are sending and you multiplex them onto a single connection. So we are talking about upward multiplexing. Now, when you're talking about multiplexing, obviously we talk about multiplexing and demultiplexing because you cannot multiplex and not demultiplex. When they reach their destination, you need to demultiplex. So the function of sending data in units, remember data is sent in segments. So when an application is sending data, it will send several segments, each segment containing some number of bytes, as we saw. When we're talking about error control, each segment contains several bytes. Okay, so the function of sending data from several connections over a single connection is called multiplexing. So you take data from different applications and you multiplex them onto a single network connection. Now, demultiplexing is the reverse, in which data which is arriving from multiple connections and then needs to be distributed to several higher level connections. And in simplicity, really what it means, let me go back to this diagram here, is that if these applications on this side, there are 3 applications. And let's assume each one of them is communicating with a different application on this side. So each one of them is talking to a different application. Now, all the data will be sent through a single network connection, or even in simple terms, they will be coming to the same IP address. Okay, and notice that the IP address will be represented, of course, by a network device. Okay, because remember that every computer is given an IP address, and the IP address is usually attached to an interface. So the data that is coming from host 2 is all coming to the same interface of a given computer. So all the data will arrive here. All the data from the 3 different applications, they will arrive here and they will be given to the transport layer. Now this transport layer will be receiving data from 3 different applications, and it needs to sort out for each data item it receives, which of these applications is it really supposed to pass that data. So that's what we are calling demultiplexing. Because the data will arrive, they have already been multiplexed, so they are mixed up. So in other words, you will have, if the data is coming in, remember they're in segments, they are segmented. So you may have maybe the first segment here is for application 1, from application 1. The second segment following may be from application 2 and from application 3 and so on. So they are mixed up, and then you have another segment here from application 1, and so on. So they have really been multiplexed onto a single network interface or connection, if you put it that way. So now it is up to the transport layer on the receiving side to sort out the data and to know application 1 wanted to talk to which application on host 1. When application 2 sent the segment, which application were they sending to on host 1? So that we are able to have proper communication. Because if we mix them up, then we are going to have problems. So I was trying to explain the multiplexing. The multiplexing is about taking them. Just a minute. Multiplexing is about taking them and passing them through one connection, one network connection, like that. So they come out through the interface of that computer, and they flow through the internet to their destination. And when they get to their destination, then this transport entity here has to sort them out. The transport entity has to sort them out so that it knows which of those applications is supposed to receive which segment. That's the idea. That's really what we are trying to find out. How does the transport layer multiplex them so that when they reach the other side, the corresponding transport layer will know how to demultiplex them? So notice, that's the last point on this slide. Without multiplexing and demultiplexing, then a user can only run one application. If we are not able to sort out the data from different applications, then we will be forced to run one application at a time on our computers. That's really what it means. If you cannot sort out this problem of how do you know which data is coming from which application, then we cannot run many applications. But of course, you know that we can run so many different applications at the same time on our computers. We can communicate with the different servers on the other side and get results, and there is no confusion. So obviously, it means somebody has solved the problem already. So that's really what we are going to look at. How was it solved? How does the transport layer not get confused about what is being sent? So a typical host will have multiple programs running, and each of those programs will need to send and receive data. That's how it is. We can run so many applications on our computers, and each one of them may be sending and receiving data at the same time. Now, all the data, as I said, must be sent using the same interface. So if you have an IP address for your computer, the IP address is attached to a network interface. So they will all flow through that same network interface into the rest of the network. So data from all applications will be funneled down initially, of course, to the transport layer, and eventually will come out through the network interface to the rest of the internet. And so that means that if they are to come out through that same interface, they will have to be multiplexed so that they can all use that same interface into the network. So what would normally happen is that, of course, the applications are running at the application layer. So the data that they are sending will first be passed down to the transport layer, which may be either TCP or UDP. And then from there, they'll be passed down to the IP layer. And then from the IP layer, they'll be passed down to the data link layer and then out through the interface. And so that's really what we are calling multiplexing. The technical term for funneling all the data through the same network interface as I've drawn it here. I think I tried to draw it. Yeah, funneling the data through, it's like sieving the data through one channel and sending it out into the network, and then receiving it and somehow separating the different data. So the multiplexing is the part where you kind of funnel them down to the same network interface. Okay, so I think I've already explained that, but let me use that diagram maybe to emphasize. So suppose we are having this computer here, that computer, and the user of that computer is running different applications. I've only drawn 3, but they could, of course, they could be more than 3. All the data coming out of those applications, if they are maybe going to a different, assume they are going to a different computer. And let me just maybe, let me even use this, because these are servers. These are representative of servers. So assume there are 3 servers running there, and each of those applications on the client computer, they are client parts, and then these are the server part of the application. So all the data from these applications will be funneled through the single network interface of this machine, that one. They will all come out through there into the network, then they'll flow through the routers and so on from there, and then they will go up. And from all the different applications, then they will come down this way, and then they will go to this server. So now when they arrive at that server, remember they're arriving at the same interface. All the data from the different applications are arriving at that interface, that network interface, because that's the IP address of the machine they are sending to. Then we need a way to make sure that the correct client here, if it's a browser, it's communicating with a web server. If it's an email client, it's communicating with an email server, so without any confusion. Okay. Now, so I have said, what I have said so far is that when data comes from the application, it goes to the transport layer. The transport layer can either be connection-oriented or connectionless. Okay? But all those packets need to be funneled down to the network interface, whether it is from a connectionless, an application using no connection, or an application using connections, it doesn't matter. All the data must pass through the same network interface. And they must be multiplexed in a way that on the other side, you can be able to tell them apart. So it comes from the application to the transport layer. If it is a connection-oriented, if it's an application using connections, the data will go to the TCP, which is the connection-oriented transport. If it's from an application that is connectionless, it will go to the connectionless transport, which is the UDP. So coming out of the TCP and UDP entities in the transport layer, they will all be funneled down to the same network interface of the machine they are sharing, regardless of whether it's TCP or UDP. So it means that these layers must know exactly what they need to put in the segments that are being sent, so that the other side can be able to know which is which. So in the process of multiplexing, some data must be put into the segments or the IP packets to enable the receiving machine to understand what has been sent and to pass it to the correct application. Now, on the receiving side, remember data will be coming from the lower layer. So it will be coming up through the data link and through the network. So when it reaches the network, it will be received by the network layer. So the network layer, of course, will be receiving data from different processes. And now it is up to the IP layer to determine, first of all, do I need to pass this data to the TCP part of the transport layer? Or do I need to pass it to the UDP part of the transport layer? In other words, was the data sent by an application that was using a connection, or was the data sent by an application that was not using connections? That's the first thing that the IP layer must sort, or the network layer. Assume it can sort that, data will either go to the TCP part or to the UDP part. Now, once it is at the TCP layer, now the TCP layer obviously knows that this was from an application that was using connections. But now there may be so many applications running on that machine that are using connections. So it must be able to decide of which of these applications that is using connections should I pass this data. On the UDP side, the UDP part may also receive certain segments, and there may be several applications running on that computer which are not using connections. So again, the UDP part of the transport layer must decide, should this data be given, which of those applications that are not using connections should I pass each segment to? So in other words, I'm saying as data comes in, goes to the IP layer, the IP layer must sort it. It must take the stream of unrelated data, datagrams, and pass them to the correct process, the correct transport process, whether TCP or UDP. And then, as I said, the UDP and TCP must pass it to the correct application. And that's what we call demultiplexing. So in demultiplexing, a stream of, that's last paragraph, a stream of IP datagrams is received and demultiplexed, and the data passed to each of the appropriate applications instance on the receiving host. So here is a diagram that tries to put that in diagrammatic form. Notice that this is explained using only the TCP, but later on, I hope we shall explain it using both TCP and TCP, or UDP and TCP. But this one assumes that all the applications that are sending, notice the arrow is pointing downwards, which means those applications, they are sending data. So whatever data they need to send, they need to pass it to the transport layer. In this case, the transport layer is the TCP one. So it passes them to the transport layer, but the transport layer must be able to multiplex them and send them to the same IP layer, which will then send them out through the data link layer to the rest of the network. So whatever data is being sent by all these programs must somehow be sent through the same interface. And then on the receiving side, data will come from the IP layer to the transport layer. In this case, there's only one type of transport layer. But if there was UDP, then some would be sent to the UDP part of the transport layer, as I've said, if there was. But in this case, they are all TCP programs using TCP. So they'll be sent to the TCP, and the TCP has to decide which of those applications the data should be passed to. That's another diagram talking about multiplexing and demultiplexing. And maybe the interesting part here is you need to look at this data here. The data is from the different applications. They are all multiplexed onto a single channel. And when they get to their destination, they must be demultiplexed to this distinct applications they're destined for. Okay. I think that's another diagram just showing now. In this diagram, obviously there's TCP and UDP. So notice that on the sending side, sending and receiving side, there's TCP and UDP. But they all use the same IP layer. So whether they are from TCP or UDP, they will all pass through the same IP layer. They will all pass through the same network interface. But they are marked. If you look at the data that is being sent here, notice that they are colored differently. That is to show they are from different applications. They are colored differently, or they are marked differently to show which application they were coming from. And when they arrive at the destination, then again, it is up to the IP layer and the transport layer to determine which application is supposed to receive what. So what we really need to find out is, how are they colored differently? What information is placed in those segments that enables the receiver to be able to demultiplex them? On the side of multiplexing, what do you really need to do to make sure that whatever is being sent will end up at the right application? So that's really what we are trying to find out. Now, of course, the benefits, as I said, of multiplexing is to make sure that you can have several higher level connections or transport connections being multiplexed onto a single lower level. So that for us is the benefit. Now, the other one is for downward multiplexing. Now, I'll skip the downward multiplexing part and just go ahead with the upward multiplexing. So you can read that. I already explained what downward multiplexing was, that you have a single transport connection sending through several network layer connections at the same time. And I said that that increases the performance. It increases reliability, performance, and efficiency. So let me not spend time there. Let me talk about the upward multiplexing and how it's done. Notice multiplexing using ports. So we come back to the ports and how they assist the transport layer to multiplex the data. Now, if you remember the header, you must remember the header of the IP packet, and you must remember the header of the TCP packet and what information is there. So I will point out the important fields that help with multiplexing. But in case you are not familiar with these fields, then go back and look at those two headers, the transport header and the IP layer header, because some data is put in the headers to make this possible. So application process multiplexing and demultiplexing is implemented using the following fields. There's a field in the IP layer called the IP protocol. In fact, I think it's just called protocol. I don't know if I have that. Yeah, this is the IP header. Now notice there is a field here called protocol. It is in the IP header. So that's where this data will be put. Now, what do you need to put in the IP protocol field? Now notice that the IP layer is running below the TCP layer. And as I've mentioned, on top of the TCP layer, you can either have TCP or UDP. So when the TCP data is to be sent via the internet protocol, then that IP protocol field will say the data I'm carrying is from the TCP part of the transport layer. Now, if this data from UDP is sent down to the IP layer, the IP layer needs to put in the same field. It needs to say this data is from the UDP part of the transport layer. So that's why you need that protocol layer. which of the transport entities provided you with that data? Is it the TCP or the UDP? So basically what is put in there is just a value. It's just a value that can distinguish between those two transport entities. Notice that there is the UDP, the UDP and TCP source and destination ports. The header for any transport layer must have the source port and the destination port, whether it is using TCP or whether it is using UDP. I think I showed you this at the very beginning, so you can look for it. There is a source port field and there is a destination port field. So those must be filled at the transport layer. So whether you're using TCP or UDP, when data comes from the application, then the transport layer must put a header around it. So whatever data came from the application, you will have to add a header. And that header will include the source port and the destination port. So remember that each of these applications running here, they are running at a specific port. So whenever they pass their data to the transport layer must put the source port in the header. Of course, because the time they were creating the connection, they also said which was their destination application and they provided the destination port, then this transport layer must also know the destination port. So it will put both the source port and the destination port. So if you look at these two applications, even at the transport layer, they are already distinguished because each one of them will have a separate or a different source port. Okay, so already they have been separated at that point. Now, when it comes to the network layer, they are already separated in the sense that, of course, these two are not separated. They are only the network layer basically says they are all from the TCP part of the transport layer. But of course, remember that at the IP layer, you also have to provide the destination IP. So if they are going to different computers, then they're already also distinguished at that point. But if they're going to the same, computer, that means the same IP address, then there will be no way to distinguish them. They will be all coming from the transport layer and all going to the same machine. So at that point, there'll be no distinction. But just notice that by saying which port they're coming from, you're already separating or distinguishing the data that is coming from two different applications. And even if they are from UDP, remember UDP also has ports. So whatever ports that are being used here will be put in the transport header as the source port. Okay, so you're already distinguishing these two data from these two applications because they're using different ports. And of course, when you put the source port and the destination port, you are also distinguishing which of these applications is supposed to receive it. Because you are saying it is supposed to go to a specific destination port. So that destination port will be used to distinguish between these two applications. So when in the sending program, you say which is the source port and which is the destination port, you're already pointing to which application you're actually sending it to. And that will be used to distinguish between which application to actually give it to. So I'm basically saying that these fields are very important in the headers of the IP layer and in the header of the TCP layer. Those fields are very important. So notice, upon transmission, the TCP provides multiplexing by using the source and destination port numbers. I've already explained that. So the TCP layer is to say which application was sending by putting the source port there. And it also says which application is supposed to receive it by putting the destination port there. So that's at the transport layer, remember. So the source and destination port numbers, of course, they are just numbers, and they are filled there to indicate the sending and receiving processes. Then, of course, the data is passed down to the IP layer. And the IP layer must now fill that IP protocol field, depending on which of the transport entities passed the data to it. So it will indicate whether it was passed through the TCP entity or through the UTP entity. So that's one field. But also remember that the IP packet must also indicate the source IP address and the destination IP address. So let's start with a situation where the packets are all going to the same IP address, the same machine. Then the source IP address and the destination IP address will be the same for all the packets leaving that computer. There'll be no distinction. They will all be carried in IP packets having the same source IP and the same destination IP. But if they are going to different computers, then they will have the same source IP, but different IP addresses. But all I'm trying to say is that the IP layer must also fill the source IP and the destination IP. And then from there, of course, they are passed down to the data link layer and they go out through the same interface. The most important thing here is that all these data, they are going out through the same network interface. On that computer, they will all pass through that interface. But having been labeled, as we have said. Now, if they are all going to the same computer, then they will all enter that computer at the same interface because that interface will have been given an IP address. So if they are all going to the same IP address, regardless of whether they were sent by application 1, application 2, application 3, or application 4, they will all enter that computer at the same interface, this one. But if they are going to different computers, then whichever other computer they are going to, they will also enter that computer at a single interface. Of course, we leave the forwarding now to the IP forwarding mechanism. So let's go to the demultiplexing side. So they have all entered through the same interface into a single computer. And now they have to be multiplexed. So the destination host will receive the datagrams. And remember that each datagram or each IP packet within itself, it contains a segment or a transport layer data unit. Now, the IP layer, of course, they'll move down from the physical layer, data link layer, and up to the IP layer. Now, each datagram, of course, will have a source IP address and the same destination address. So it will have a source IP address and a destination IP address. So here the destination IP address is important because it's what has caused it to be brought to this particular machine, the destination address. So they will all be having the same destination address, IP address. And of course, they will be having separate source and port numbers. So the destination host, that's the last point there, uses the IP addresses and the port numbers to direct the segments to the different applications. So what does the receiver do? The first thing it does, the IP layer, it looks at the protocol field. For any data item it receives, it first looks at the protocol field. Once it has looked at the protocol field, it will know whether it should pass it to the TCP entity or to the UDP entity based on what was filled at source. So once it knows that, of course, remember it will remove the header and then just pass the segment. So it will remove the IP header after knowing which field, which of those entities it should pass it to. So it will pass the datagram to the appropriate transport protocol, whether TCP or UDP, based on the IP protocol field. Now, what does the transport layer then do? Now, when you look at the transport segment, we say that it has both a source port and a destination port. So once the data is passed to the transport layer, it now looks at the source, at the destination port. Based on the destination port, although it's not that simplistic, it will be a combination of both source and destination, but it looks at the destination port, and based on the destination port, it passes it to the correct application, the application that is using that particular port. And that means that the data will end up at the correct application. So that's really what demultiplexing and multiplexing is about. Filling in those specific fields. The source port, destination port, the IP protocol field, the source IP address, and the destination IP address is enough to send data to its correct application at the correct machine. Okay. You can look at that question, which basically says, explain step by step how demultiplexing will take place. Notice demultiplexing. So think about what I've said about demultiplexing. I've said, first you look at the protocol IP field, the IP protocol field, so that you pass it to the correct transport entity, whether TCP or UDP. Once it is at TCP or UDP, you then look at the source port and the destination port, and you pass it to the correct application. Okay. Any questions on that demultiplexing and multiplexing process? Mm-hmm. Mm-hmm. And to do what? Application 1 and 2 have what? Mm-hmm. 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 I'm not sure I've understood your question, but I think you are asking application 1 and application 2 are both talking to the same server, the same application on the receiving end. Okay, fine, then they will just be sent to the same application. But remember, if it is TCP, if it is using TCP, the two applications will have created a connection. And remember we said, when they reach the destination, each of those connections has its own queue. Each of them will have its own distinct queue on which its data will be placed. Remember, we say that it is the application to pull the data. If the application chooses not to pull the data will have to sit in the queue. So we obviously can't implement them using the same queue. we must have separate queues. Even because they have all made this different connections to the same application. But at the application end, their queues must be separate. So that the data will be sent, when the application begins to pull the data, it will pull them in the correct order. Because remember, there's also the error control. The data is being sent and it must be received in the same order. I think we saw that in our last class. They must be received in the same order. So they will be in those queues in the order in which they were sent. And if there's any one of them that got lost, it will be requested for, and the others will have to wait until they are all put in order. But there's obviously a certain, I mean, and that's a good question because I think you are looking forward. There's just some detail I have not yet given you about how the server really operates. But in a nutshell, let's just assume the server has two different queues. For now, that will be sufficient, I think, to answer your question. But it is a little bit more detailed than that. I don't know if that answers your question, by the way. Okay, fine. All right. So now we want to answer these questions. We are entering a section where we need to answer these questions. How many clients can a TCP server connect to? How many connections can a client have to a single server? We need to answer those questions, and that will help us with the multiplexing we are talking about. So we are really asking, if I have a server on this side, and I have clients on this side, how many clients are allowed to connect to this server? How many? Is there a maximum? That is the first question. The second question is, if you are a client machine, okay, how many connections can you have to a single server? So here is the server, here is your machine, which means you can run many applications if you want. You can run many applications. So how many connections can come from your machine to a single server? How many can you make, or should you make? Is there even a maximum? Is there a maximum? And these are different client machines. So those are different client machines. How many different client machines can connect to the same server? That's question one. The other one is, if I have a single machine and I'm running many applications on my single machine, how many connections can I make to the same server? Those are important questions, and that's really what we are trying to answer. So let's hope we can answer them. Now, remember, we set up connections using port numbers. I think we've talked about this before when we are saying that when you need to create a connection, you need to have a connect command. And we said that in that connect command, you must put a variable there that says which server you want to connect to. So that server that you want to connect to, you will specify it using the composite address. You specify the port number of the server and the IP address of the server. So obviously, setting up connections, you must use port numbers to set up a connection to any server. So we are assuming a client server type of connection. Now, so the port numbers will allow TCP to set up virtual connections. Now, each source and destination port pair identifies a separate virtual connection. In other words, if you have a source port here and you specify a destination port here, each of these, even if it is the same server, assume they are all connecting to the same server. So the destination is the same, but the source port is different because different applications must run on different port numbers. So if the first application has port number 1, the second application has port number 2, the third application has port number 3, but the server port is port 80, let's assume it's a web server, then the combination of port 1/80, port 2/80, port 3/80 gives you 3 different virtual connections. In other words, you can distinguish them. Because even though the destination port is fixed, the source port is variable. So you can distinguish those different connections based on the source port and the destination port. So each source and destination port pair identifies a separate virtual connection, allowing you to have multiple connections. As long as you can distinguish your connections, you can have multiple connections. However, remember that every socket is identified by 2 variables, the source port, not the source port, the port number and the IP address. So ultimately, you will find that different connections are distinguished not only by the port numbers, the port number pairs, but they are distinguished by 4 numbers, four numbers, because this application that's running on this side, let's, let me get my pen. This application that is running on this side, it has both an IP and port number. It is identified by both the IP address and the port number. So even if they are on the same IP, remember that these programs I'm saying may be running on the same computer. So they both have the same IP, but the port numbers are different. Because on the same machine, you cannot have 2 programs running on the same ports. That's not possible. So assume the IP address part is fixed. Even then, you can distinguish the connections because you'll have the same IP. Let's assume the IP is 192.168.1.3, but the port numbers will be different. And then on this side, you'll also have this application having, you'll also have this application here having the same IP address. So the IP is fixed and the port number is fixed if it is the same application. But because the identification of a connection is based on those 4 variables, the source IP, the source port, the destination IP, and the destination, this should be destination IP, not port. This should be IP. Because it is based on those 4 variables, each of these connections is different. Notice that the IP of the destination and the port of the destination is fixed. And notice that the source IP is also fixed. But because at least there is 1 variable in all those connections, you can distinguish the connections. But what I'm trying to say is that a connection is set up using port numbers and IP numbers, and there are 4 variables required to distinguish any connection. So the multiplexing will be done using those 4 values. the multiplexing is basically done based on those 4 values. For every connection, you will have to know its destination IP, is source port, destination address, and destination port. So the multiplexing is done using those 4 values, and even the multiplexing is done using those 4 values. And remember that those 4 values are able to distinguish a given connection fully. They make a connection unique so that there's no confusion about which connection you're talking about. Now here I want to distinguish the passive port and the active port. And we've already said this, the server port is always passive because the server just sits there waiting to be requested for information. So it's always the passive side. So you may call the port of the server to be a passive port because a server basically listens, and it always listens only on one port. Yet it can have many, many clients connecting to the same server, and the server will never confuse which client has connected to it. It cannot confuse, but it listens on one port and it answers on that one port. But because of the 4 values I've told you about, the server can never mistake which port it is dealing with or which client it is dealing with, because on this side, the server will have those 4 values for each of the connections. It will have the source IP, the destination IP, the destination port, the source IP, and the destination IP. For each of these connections from the client, that value is stored at the server side. So it always knows which client am I dealing with. And there will be no confusion about it. But anyway, the server is passive, as we said. The server is passive, and it must have a unique ID for each of the simultaneous connections from the clients. Then, of course, the client is the active one because it's the one that makes a connection to the server. It's the one that initiates a connection to the server. So we also need to find out, how does the client distinguish the many connections it can make to a server? How can it distinguish them? Also, of course, based on those 4 numbers. Based on those 4 numbers, it will be able to distinguish each and every connection that it's making to the server. But remember, on the client side, it is the operating system that chooses the port number to avoid a client reusing a number without knowing. Yeah. So on the client side, if the client is making several connections to the same server, remember that this will be fixed. If the applications are on the same client machine, then this IP address will also be fixed. But the port number can never be fixed because different applications will talk through different port numbers. So even though the server port and server IP address and client IP address may be fixed, the connections will still be distinguished by the one variable, which is the client port number. It will make the different connections unique. But if they happen to be on different computers, then the IP address may also be a variable. But either way, these 4 values are able to distinguish the different connections you make to the server. I'll leave that issue of file descriptor to the next time. So now I think what we have really looked at is, how do you distinguish connections? Because what we want to answer is this question here. How many clients can a TCP server connect to? What is the maximum? I think we are asking, what is the maximum number of clients that a server can connect to? What is the maximum? And how many connections, or what is the maximum number of connections that a client can have to a single server? That's really what we are asking. That's the question we want to answer. But before we answer that question, we have basically said that we need to know how then do we distinguish a connection? How do we distinguish connections? A connection is identified by 4 values, as I've explained. And as long as there's one of those 5 values that is variable, it can be used to distinguish them many different connections. So now we need to go further and answer that question. How many connections can a server accept? And how many connections can a client make? Is there a maximum? Now, I think because of time, we will stop there. So next time we come, next class, we'll try to ask, what is the maximum? Connections from clients, and we will try to answer what is the maximum number of server connections that we can have based on what I have explained today. So any question on how you distinguish connections? Any question on how both the client and the server are able to distinguish the connections? Okay, if that is clear, then to answer that question will be very simple. And I think before the next class, all you need to ask yourself is, if connections can really be distinguished by the one variable called the port number, how many ports can you have on a single computer, on a single client? How many ports can you have? What is the maximum number of ports you can have? That will answer your question. Because here, if everything is fixed, we are noticing that the port number is variable. And that variable will enable you to make the different connections. So what is the maximum number of variable port numbers you can have? And next time you will tell me. You come with that answer, and then we will answer those 2 questions.